Hi, and welcome back to clip 3 of this series of AS Kinetics discussions. And again, we're starting immediately with a Maxwell-Boltzmann distribution, showing the most probable energy of a sample, of a gaseous sample, being at this energy here. And again, we'll just very quickly highlight the activation energy, which indicates the number of particles which have the activation energy, demonstrating that very few particles will lead to successful collisions under these conditions. And in this third clip, we're going to now look at how the distribution changes when we change the concentration of a sample. So in the previous clip, we changed the temperature but kept the concentration the same. In this one, we're going to keep the temperatures the same, but this time change the concentration. And we're going to approximately double the concentration of one of the reagents that we're looking at here. And it's important then to think that the shape of the graph is going to remain the same. And by that, what I mean is, because we're not changing the temperature and subsequently we're not changing the energy of those particles in our reaction, the most probable energy, i.e. the peak of that curve, is going to stay in the same position. If we are going to double the concentration, what we are going to do at each point on the graph, we are essentially going to make it twice as high. And we are going to get an approximate position like that, whereby at each energy of a random particle in our sample, it's approximately twice as high at each of those points. And so the most probable energy here is about twice as high as there. Now, obviously, it's an approximation to some extent, but having some control of the diagram allows you to draw quite accurately within the ability of ourselves to draw. It shows how the distribution changes, or importantly for concentration, how the distribution doesn't change. We're not changing the overall energy of the particles, we're just changing the number of particles. But in terms of our activation energy, what that then means is that we have now got twice as many particles. If we, as we said, doubled the concentration, we now have twice as many particles with the desired activation energy. So we should see a subsequent increase in rate. So the rate will increase due to more particles. Now, if we have doubled the concentration, we could approximate that we've now got double the number of particles with the activation energy. So we may see a doubling of the rate. Obviously, when we look at further clips with rate equations, it's not necessarily true, but if we assume a first order reaction, then we would see that conclusion. So a rate will increase due to more particles having the desired activation energy. And what we are seeing is, though, not the same number of particles, or not the greater number of particles in line with what we saw with temperature. We're simply seeing here just a doubling. We're not seeing this many more, significantly more particles, just a straightforward doubling of the number of particles with the activation energy based on a doubling of concentration. But it's important to see that the position of this peak maximum here hasn't changed. It's in the same position as it was here. And it's important to also see that the activation energy also hasn't changed, because we haven't changed the temperature, we haven't changed the presence of a catalyst, and so the profiled shape of the Maxwell-Boltzmann stays the same. It's just the height of it has now, in this example, doubled. Likewise, if it had trebled, it would be 3 times higher, or indeed if we'd halved the concentration. And so remember in some past papers that you can attempt to draw the diagram quantitatively if a question gives you sufficient information along that way. And in the next clip, we'll have a look at how the presence of a catalyst also changes this diagram, and again, how it can then subsequently affect the rate of reaction. Thank you very much again, and I will see you in clip number 4.